We know that if we're solving an oblique triangle and we're given one angle and side opposite pair, that we use the law of sines to solve the triangle. Well, if we're not given that information, that is, if we don't have an angle side opposite pair, we have information, just one bit of information about every angle side opposite pair, then we need to use the law of cosines. And it goes like this. That, now, we understand that A, B, and C are the lengths of sides, and uppercase letters are the size of angles. So this is the one side squared is equal to the sum of the squares of the other two sides minus 2 times the product of those other two sides times the cosine of the angle opposite that side. Kind of an interesting relationship here. And this is just one of 3 versions of the same thing. Now, you know, if we were, for example, I'm using side A here that we're sort of solving for or writing this in terms of. If I were writing it in terms of B, it would be B squared equals the sum of the squares of the other two sides. That would be A squared plus C squared. Then minus 2 times the product of those two rascals, AC, and then the cosine of the angle opposite B, oh, that's angle B. And there's a third version as well. You only need to remember one of them, though, and just kind of understand the structure. Now, if we take this law of cosines and we solve it for cosine A, you see, we kind of solve it for the angle, then we get this form for the law of cosines. So sometimes we'll be solving for a side and sometimes for an angle. And if we're looking for an angle, we want to use this version then of the law of cosines. I think it's kind of interesting with the law of cosines. It looks so much like the Pythagorean relationship up to this point that if you investigate it a little bit, you find out that we could actually use the law of cosines instead of the regular Pythagorean relationship, because if this is the hypotenuse squared, then understand that the angle opposite the hypotenuse is the right angle in a right triangle, you see. So we'd have, let's see, the hypotenuse squared is equal to the sum of the squares of the other two sides minus 2 times those other two sides times cosine of a right angle. Well, the cosine of 90 degrees is 0, so this term completely goes out and we have the Pythagorean relationship as we might expect. Well, consider this problem. Here we have A is 8, B 19, C is 14, all in feet. Now notice that we're given information about A, B, and C, the lengths of the sides of a triangle. And we want to solve the triangle, so we want the size of the angles involved. Now, in terms of angle side opposite pair, we don't have information about some angle and side opposite pair. So we have to use the law of cosines. Since we are finding the size of an angle, we're going to use this form of our law of cosines. That is, the cosine of an angle is equal to, and then we write that fraction. Now notice in the fraction we have the sum of a couple of sides, you see, not related to the side opposite that, and then minus the side opposite that squared, and then over 2BC. And the BC are the same as those in the numerator. And you'll look for patterns like that in order to try to recall the law of cosines in the two forms that we talked about. Anyway, it's a matter of just replacing letters with numbers and punching the calculator pretty much. So we have, let's see, cosine A would give us all of this business, and we want the angle whose cosine is this number. So we want inverse cosine of that number, and we find A then to be approximately 22 degrees. Okay, now what do we do? Well, we could go through and use the law of cosines to solve for the other angles, but you know what? We have an angle and side opposite. You see, we have that angle side opposite pair, so we could use the law of sines here to find other information in our triangle. And that's generally what you'll probably want to do. It's generally the law of sines is a little easier to use than the law of cosines. So we would, from this point, go into the law of sines to solve for the rest of the triangle. Let's see how that would work. Well, we have this angle side opposite pair, so we need the other angles involved. Let's find angle B. So it would be sine B over B equals this angle side opposite pair that we already have. So it's sine B over 19. and then angle side opposite pair. Now we figured this to be 22 degrees. I do want to mention though that if you're making this calculation, you would probably want more accuracy than just some kind of whole number of degrees here. You'd probably list this as some kind of longer decimal here just for greater accuracy, and you'd probably list that angle down there a little more accurately as well. But at any rate, we get down to the point in the problem where we find the angle whose sine is this fraction to be 63 degrees. But in the last section we came to realize that there are a couple of angles whose sine would be this. There's one that's acute and there's one that's obtuse. And that obtuse one lies in the second quadrant, and it is the supplement of this one. So you take 180 and subtract this and you get 117. Now which one is it? Well, gee, there shouldn't be any ambiguity here, because after all, we were given the lengths of 3 sides of a triangle. There's only one way to put together the triangle. So how is it possible that we would have a case where we have 2 situations? We have only one situation. Now, which one is it? Well, it turns out that we can decide which one it is by attacking the problem a little bit differently. Let's come back to the beginning and just look at it. Now, we have the lengths of 3 sides given initially in the problem. And if we just realize that the structure of triangles is such that the largest angle in a triangle is opposite the longest side. The largest angle is opposite the longest side. Then what we should do is attack this problem by solving for the largest angle. The largest angle being the angle opposite the side that's 19. So we want angle B. We want to solve for B to begin with. And you see, if we find that B turns out to be obtuse, then we know that the other 2 angles have to be acute. And we know that if angle B is acute and it's the largest angle in the whole triangle, then the other 2 are acute. So in either circumstance, once we find that first angle, we know that the other 2 are acute, and then we only have one circumstance to deal with when we use the law of sines. Okay, so here's how we would approach the problem. Let's erase this, forget that. Let's suppose we start the problem from the get-go. All right, so we have the lengths of all the sides of the triangle. Now we decide that this is the longest side, so we're going to solve for the angle opposite that side, and that would be angle B. Now, notice that this is a version of, and there are 3 versions of, the law of cosines in this form. It could be cosine B right here, cosine A, or cosine C. And we have to kind of structure the fraction over here accordingly. We have the different sides here, and the one that's being subtracted, this minus B squared, the B is opposite that angle. That's the kind of the important key point here. And the AC, the 2 sides in the denominator here come from these 2 rascals in the numerator. Okay, so that's kind of how you'll remember it. Anyway, just plugging in the information, we find cosine B to be this fraction, and now we want the angle whose cosine is that, so we want inverse cosine of that fraction, and we find it to be approximately 116.8 degrees. So it's obtuse. So that means then that, oh, and by the way, I almost forgot to mention, there's only one angle here when we're using this law of cosines. When we come to an answer right here, we don't have this situation where we have the possibility of a first or second quadrant angle whose cosine is the same value and stuff like that, like we did with the law of sines. And that has to do with, well, it has to do with a lot of discussions that we had before. But remember that the domain for our values here, our angles, when we talk about cosine, fall into first and second quadrant. You see, and so we have kind of built in the idea that we can have either acute or obtuse angles that emerge from the calculation. Okay, so we don't have that ambiguous possibility here when we use this. All right, so we have an obtuse angle here. One of the angles is obtuse, the other 2 must be acute. And so we can go through and use the law of sines without the ambiguous possibility. Okay, now let's find the other angles. Let's find the angle opposite, let's say side A. So it would be angle A. So we write sine A over A equals sine B over B. We just found the size of that angle. So B is 116.8, side B is 19, side A is 8. And then multiplying by 8 on both sides, we get this fraction. So we want the angle whose sine is that fraction, and we find that angle to be approximately 22.1 degrees. And notice I'm using a little more accuracy here in this problem, and really you can use whatever amount of accuracy that you want to in problems like this. You can carry this out to 3 or 4 decimal places. Just be consistent from problem to problem when you do that. Also, I would suggest that when you plug in the value here for this angle, that you use a few more digits here to describe this angle. That'll give you a little more accuracy as well. Okay, at any rate, we find angle A to be 22.1 degrees, and we need not worry about a second quadrant reference angle of 22.1 degrees and all of that business. We know that we have an acute angle here within our triangle. And then for angle C, it's 180 minus the other two. So it's 180 minus 116.8 minus 22.1, or approximately 41.1 degrees. Suppose we want to solve a triangle given this information. We have the size of an angle and we have the length of a couple of sides. And we would look to see if we have an angle side opposite pair. No, we have angle A, but we don't have side A. That tips us off that we need to use the law of cosines. Now, in the previous example, we were given the lengths of all 3 sides, and then we used the idea that we were going to solve for the angle opposite the longest side, and we kind of get mileage out of doing that. But what do we do here? What side or what angle do we solve for? Well, we end up solving for the side opposite that angle, because it's easy for us to structure the equation for the law of cosines. You know, we only have the cosine of a single angle when we are writing the law of cosines in one of its forms. And the side that we're solving for is the side opposite that angle. So we're going to solve here for side A, and we set up the law of cosines like this. It is A squared equals the sum of the squares of the other 2 sides. That's B squared plus C squared, and then minus 2 times those 2 sides times the cosine of the given angle. It's A in this case. It's the angle related to that side. Okay, so that's how we write the law of cosines. Then it's A squared, now we're just plugging in, is 3 squared plus 10 squared minus 2 times 3 times 10 times cosine 55 degrees. And when the smoke clears on this calculation, A squared turns out to be about, and it's a pretty long decimal, but it's about 74.5 and so on. And then we want the square root of this for A to be approximately 8.6, let's say. Now again, I say let's say because it goes on and as a decimal, and I'm rounding it off to the nearest tenth. Now we would decide to solve for the other aspects of our triangle. We need a couple of angles, and we need, we have the third side, so we need the other angles, and that's all there is to it. Let's solve for angle B. So we'd have sine B over side B is sine A over side A. So side B is 3, that's given information. The angle of 55 degrees, we know that the size of one of the angles to be 55 degrees. Side A is opposite, and that's what we just solved for. Now, it was 8.6. We approximated it as 8.6, but we would use a longer-winded decimal here. Or I'll tell you what to do as we get into the calculation for this angle B in just a second. Multiplying on both sides by 3, we have this fraction. Now, we want to evaluate this fraction and take the inverse sign of that value. Now, here's what you want to do. If you have the long decimal already on the calculator from the previous calculation, then what you can do is rather than re-enter this in the context of this, that is, rather than start over on your calculator and say 3 times sine 55 divided by this number and have to re-enter this, just press the reciprocal button. If this is already on screen, press the reciprocal button, because it turns out that dividing by some number is the same thing as multiplying by its reciprocal. So what you're doing in pressing reciprocal is you're putting this into the numerator as a factor. You're putting this information about dividing by this number into the numerator as a factor. And then you multiply times 3 and then times sine 55. And you're getting the most accurate value you can find for sine B. And then you want the inverse sine of that number, and you find B then to be approximately 16.5 degrees. Anyway, just a little helpful technique there, I hope. The third angle is found by taking 180 degrees and subtracting the other two. So we subtract the given angle and the one that we just found to be 16.5 degrees, and we find C to be 108.5 degrees. Well, before we leave this problem and this topic, the law of cosines, I have a story to relate to you. It's a short story, but it's a true story. Some years ago, a gentleman walked into my office. I was teaching at a local junior college. And this gentleman walked into my office and he asked that I look at a set of plans. He identified himself as someone who worked for a local construction company specializing in building roads. So he was with an engineering firm. All right, so I looked at his paperwork, and he laid out this most elaborate set of blueprints you ever saw in your life. I mean, there were lines going all over the place. And he identified a very specific point on this big elaborate diagram. And he said, I'd like to know the distance from that point to this one right here. I said, and it wasn't given directly, but there were things going all over the place, relationships here and there and everywhere, and it was a difficult problem to figure out. And so I said, well, leave the plans with me and I'll study it a little bit and see if I can figure that out. And I said, what method are you using now to figure that out? He says, well, we use a computer-assisted design, a CAD program to do that, and we can get it within a few millimeters, but we want an exact value. I said, that's interesting. Okay, so I go through and I look at it, and after pondering the problem for about 45 minutes or more, I discovered a triangulation involving 3 bits of information. And I discovered then that I could use the law of cosines on the problem. And so I did, and I got an exact value. That's not the point of the story. The point of the story is the guy came back, I gave him the answer to the problem. He said, how did you figure it out? I said, I used the law of cosines. He says, you know, I took trigonometry, and I don't remember the law of cosines. And he said, now that you pointed out to me, though, I do seem to recall it. I use the law of sines all the time, he says, but the law of cosines, I just didn't think about it for this particular problem. Now, the point of the story is that the law of sines and the law of cosines adds much to our mathematical toolbox. And that's all that we're doing in studying math and going from topic to topic. These are not specifics that you're going to remember. You're not going to remember the law of cosines 3 weeks from today as you're looking at this. You're going to take the test and then you're going to forget it. But if you just realize that it exists, you can always come back to a trig book and you can look up the law of sines or the law of cosines and you can make use of them. So, and because you have had the experience of these things before, it's going to be relatively easy for you to get back into the use of them again. Anyway, good luck.